Okay, it's 8 o'clock. Good morning, everybody. Let's see. I returned your exams, and they're pretty good on the whole. Although, okay, people tended to either do really well or not do well at all. There wasn't a whole lot in between. The average is about 75. So, um, actually, I was pretty happy with them. Some of you really need to work on your algebra. This algebra thing's gonna get you. It's not gonna go away. If you're weak on your algebra, you need to work on it. It's gonna come back and come back and come back if you don't. Also, one thing with me, always make sure you add the number of points that you missed and make sure I added correctly. Okay.
Ms. Kennedy, I just checked my emails, and there's no attachment to the one you sent me.
Okay.
It just says to Britton Drake, and that's it.
Okay. Who did? Okay. They're supposed to have been. I will. Okay.
I'm not sure if that's because it was identified as junk or not.
Well, okay, if your email identified it as junk, I can't do much about that.
Well, that's fine. I can access junk mail, but I was just wondering if that's why there was no attachment to it. To it, if it trashed the attachment, it was identified as junk.
I will check and I will try to resend it.
All right.
Yeah, you should have gotten your graded exam back. And if you didn't, I will check. Okay. So let's see. Any questions before we get started here? Okay. Let's get started then. Okay. All right. We talked about implicit differentiation yesterday, and a little bit the day before. And we're going to use this to get derivatives of the inverse trig functions. Okay. As I mentioned, the trig functions really don't have inverses because they are periodic and therefore not one-to-one. Okay, so for example, sine function looks like this. Okay, this is pi 0, 1, and minus 1. It's not one-to-one because a horizontal line there was going to cross it an infinite number of times. So in order to get an inverse, you have to cut it down. Okay, which works to some extent, but it does lead to problems sometimes. I'm not going to focus on the problems today. We're going to cut this down. We're just going to keep this one piece right here. And this is the sine function. Okay, I'm going to just keep this red piece. And I'm going to call that the cap sign. So And what I did was to restrict the domain. If minus pi over 2 is less than or equal to x is less than or equal to pi over 2. So the domain of this cut down function somebody entered late, of course. And the range is still minus 1 to 1. Okay, let me go back and let him in. Also, I forgot to start the recording. Okay. And now I'm going to go back to my screen. Okay, so we've cut down the sine function. We call this the cap sine. And okay, now it's 1 to 1. And that means it has an inverse. So we're going to call the arc sine. Oops. Okay, now I mentioned yesterday, you'll also see this notation. I hate that notation because, okay, it's ambiguous. When you write this, you mean sine of x times sine of x. And when you write sine cubed of x, you mean sine of x times sine of x times sine of x. If you write sine to the minus 1 of x, how come that doesn't mean 1 over the sine of x? Well, reading that, it should mean that, okay, and not the inverse function. So this is just bad notation. In mathematics, you want to know exactly what you're talking about. Exactly. No confusion. I don't want to take 1 over the sine of x. I want to get the inverse function. And that means I want to flip all the ordered pairs. Okay, so this point right here, the starting point is minus pi over 2 minus 1, and the ending point for cap sine is pi over 2, 1. And the inverse function you obtain by flipping the ordered pairs. So the arc sine is going to have the point, well, instead of minus pi over 2 minus 1, it's going to have the point minus 1. Whoops. Got my eraser on, okay. It's going to have the point minus 1 minus pi over 2. Pi over 2 is about 1.57, something like that. And sine of 0, 0, so that's on there, and 1. That's pi over 2. Okay. Pi over 2, sine of pi over 2 is 1. It looks kind of like that. Okay. So to get this curve, I just flipped all the ordered pairs on this curve. That's what you do to do an inverse function. Okay, so we have sine of x is y. That means if I take the inverse function, arc sine of the sine of x is the arc sine of y. Well, the arc sine of the sine, these are inverse functions. So I take the sine and then I undo the sine. And that gives me x back again. As long as, okay, my x is in the appropriate interval. But okay, so I've got the arc sine of y is x. And I can think of this as an implicitly defined function. Oh, I should have switched variables. Okay. Okay. So I want to know I want to find the derivative of this function. Okay, so now x is my independent variable. When I say independent variable, this is the one you choose, okay? And then once you choose x, then y is completely determined. Okay, so and y is a function of x. Okay, so I've got y equal to the arc sine of x, and then that means that if I take, okay, what's y in, let's see, what do we say? The arc sine function has domain -1 to 1, okay, and range minus pi over 2 to pi over 2. Okay, so I have this well-defined function, and I want to find its derivative. All right. Well, if I take the cap sign of y, well, apply the cap sign to both sides. On the right-hand side, I have the inverse of the function and then the function. So I take the arc sine, then I take the cap sign. That just gives me x back again. So I have the sine of y is equal to x, and I have y defined implicitly as a function of x. Somebody just entered. Okay. Okay. So I'm going to take the derivative of this thing, treating y as a function of x, and a y defined implicitly, and let me go let Mr. Perez in. Okay, so I've got to go back. Okay. Okay, now let's go back and share the screen. Okay. Okay, so now we're down to sine of y is equal to x. Well, the thing about this is I know what the derivative of the sine is. And although cap sine, well, I cut down the sine to get cap sine. I chopped it down to an interval on which it's 1 to 1. But that's not going to change the fact that the derivative is still cosine. So differentiating implicitly well, the derivative of x is 1. Remember, x is my independent variable. The derivative of the sine of y is, I have to use the chain rule, because y is a function, y is inside the sine. Derivative of sine is cosine of y, but then because y is a function, I have to multiply by y prime. So y prime is 1 over the cosine of y. Okay, so we have the derivative of the arc sine. But it's in terms of y. And that's not real satisfying. So let's see. If the sine of y is x, then I can set up a triangle. Remember, sine is opposite over hypotenuse. Okay. And if the sine of y is x, well, that's x over 1. And I can label the opposite side of the triangle as x and the hypotenuse as 1, which means that this side, by the Pythagorean theorem, is the square root of 1 minus x squared. So that'll allow me to get rid of the y and, well, write it in terms of x. The cosine of y, just looking at this triangle, the cosine of y is adjacent over hypotenuse. So it's 1 minus x squared over 1. And there we have it. If y is the arcsine of x, then y prime is 1 over the square root of 1 minus x squared. Questions?
I do have one, which isn't 1 over cosine of y equal to, I believe it would be secant of y.
Yes. Yes, it is. And that would be also 1 over, so that would be hypotenuse over adjacent, and that would give you 1 over the square, give you the same thing. Yes, it is. 1 over the cosine is equal to the secant.
Okay, thank you, ma'am.
Okay. Anything else? Okay. Well, okay, so this is everybody agrees that to get the arc sine, you should cut down the sine the way we did. Okay, just keep this little red part here. Everybody agrees about the tangent thing too. Okay, the arc tangent, the inverse of the tangent function. Unfortunately, everybody does not agree about the secant and the arc secant. So, okay, let's do the tangent. Okay, so tangent. First of all, let's just draw it. I hope you have these pictures in your mind. These functions, these important functions. Tangent, again, it's periodic, therefore it's not 1-to-1. So what do? Well, we throw away everything. Well, throwing away, this can get you into trouble in math. And this sometimes does, but okay, we're going to throw away everything except this piece. So we're going to cut down the tangent. To get what's, okay, I'm going to call the captan. And for this function, so I'm going to require that you keep the domain to be minus pi over 2 to pi over 2. And on that interval, that if you throw away everything else, you have a 1-to-1 function. So, and let's see, captan. It's going to be, in fact, all real numbers. Because of the asymptotes there. Okay, so now this new function is 1-to-1 because I threw away all the other pieces. If you have a 1-to-1 function, you can get an inverse. Okay, and the inverse and I'm going to call it the arctangent. And I get the arctangent by flipping the ordered pairs and the tangent. Okay. So 0, 0 is on the captan. That means 0, 0 is going to be on the arctangent. The tangent of pi over 4 is 1. So pi over 4 1 is on the tangent function. That means that 1 pi over 4 is going to be on the arctangent. The vertical asymptotes are going to become horizontal asymptotes when I flip those ordered pairs. So now I'm going to have horizontal asymptote at pi over 2 and minus pi over 2. There. And why am I doing that? Okay. That's supposed to be a point. Okay, so pi over 4, 1 is on the tangent. That means 1 pi over 4. Pi over 4 is a little bit less than 1. I'll call it that. Okay. And minus pi over 4 minus 1. It looks kind of like this. Okay. So that's the arctangent function. And because the domain of the captangent is the range of the arctangent, and the range of the arctangent is the domain of the, okay, which one did I say? The range of the tangent becomes the domain of the arctangent. So the domain of the arctangent is all the reals. And the range of the arctangent is the open interval from minus pi over 2 to pi. Okay, so we have this new function, the arctangent of x, and we want to get its derivative. Okay, well, I don't know how to find that, but I know what the derivative of tangent is. So I'm going to take the tangent on both sides.
The answer would be tangent, wouldn't it?
Pardon?
The answer for this one derivative would be tangent, wouldn't it?
The answer? Well, the tangent certainly related. Okay. Yeah. Oh, somebody else is in the waiting room. Okay, let me go back. Okay, mull over that while I let somebody in.
He must have disconnected because I had literally just seen him on the side of my screen where it shows everyone's faces and such.
Okay, Mr. Libby, I didn't get that. You kind of faded in and out.
Sorry, I was saying that the person you just let in must have had his connection lost because right before that showed up, he was still in the classroom for me.
Right. He just sent a chat. Okay. Yeah. Good old technology. we just have to do what we can. Okay, there are problems on my end sometimes. Yeah, in my second class, a couple of times my internet's crashed. Ugh. If that ever happens in your class, just stick around. I just have to reboot, but I'll be back. Okay, the Zoom meeting won't kick out. Okay, that's totally beside the point. But let's go back to our discussion of inverse trig functions. I'm learning not to freak out so much. These things happen. Okay, so we want to find the derivative of this new function. Okay, y equal to arctan of x. Well, I'm going to use the fact that the inverse of this is the tangent. Well, it's a cat tangent, actually. But, and I stuck in arguments, okay. But, okay, so I cut down my tangent function to get cap tangent. Does not change what the derivative is. But okay, I'm taking the cap tan of y is the cap tan of the arctan of x. When you take a function of x and you take the inverse of it, okay, you do something to this number and then you undo what you did to it, you get back x itself. So we have cap tan of y is x, and the derivative now, so y is a function of x defined implicitly in this equation. Y is my function, okay? X is the independent variable. And that means, okay, the derivative of x is just 1. But on the left-hand side, I have the function y inside the function cap tan. So the derivative of tangent is secant squared of y. But since y is a function and not just a variable, I have to use the chain rule, and that's secant squared of y times y prime. So that gives me that y prime is 1 over the secant squared. Okay, so I've got the derivative of y, only it's in terms of y, which is not terribly satisfying. But okay, I'm going to use the fact that the tangent of y is x. So think of y as an angle. And tangent is opposite over adjacent. So I can label the opposite side as x and the adjacent side as 1 in my triangle. And that means the hypotenuse is the square root of 1 plus x squared. And then I can use the triangle and just read off the secant of y. Y prime is 1 over the secant of y is the square root of 1 plus x squared over 1, but that all gets squared. And that's just, well, okay. Dividing by 1 just gave you the number back. And when I square the square root, those are inverse functions too, I just get 1 plus x squared back. So y prime is the derivative of the arctangent function is 1 over 1 plus x squared. Okay. So far, we have now the derivative of the arc sine. And we have the derivative of the arctangent. What about, okay, well, the secant and the cosecant are matters of contention. Let's talk about, you're rarely going to see any mention of this function, the arc cosine. Let me show you why. Okay, but certainly cosine. Okay, cosine, let's draw it first. Cosine of 0 is 1. And goes on forever. And let's see. So that's the cosine function. Well, it's periodic. It's not 1-to-1. In order to take an inverse, you got to cut it down. So what do we cut it down to? Well, pretty much everybody agrees that we should take this interval right here. Okay, so that gets the whole range, but cuts down the domain to just one interval on which this thing is 1-1. Let's say, so we get the cap cosine of x is y. Okay, just putting in an argument there, and then calling the cap cosine, naming it y. Okay, so I cut it way down. So the domain 0 has to be less than or equal to x is less than or equal to pi. And the range still minus 1-to-1. Okay. Okay, but if I cut it down that way, now it's 1-to-1. So it has an inverse. And we're going to call that the arc cosine. Okay, so to get the inverse function, you flip the ordered pairs on your original function. So let's see, ordered pairs. 0, 1 is on the cap cosine. And then pi minus 1, and then right in the middle there's pi over 2, 0. So I'm going to flip those, and that means in particular 1, 0, 0 pi over 2, and minus 1 pi are all points on the arc cosine. Okay, so what does that look like? The arc cosine has domain minus 1-to-1 and range 0 to pi. We flip the ordered pairs, so the domain and range flip too. And okay, so 1, 0. Let's make this blue. 0 pi over 2 And, oh, no, 1, 0. That was, let me do that again. Okay. 1, 0 is that point. And minus 1 pi, that point. So we're going to get a curve. Looks kind of like that. Arc cosine of it. Okay. So we have this function, well defined, because we cut down our cosine function so that we kept the one-to-one piece of it. We flipped the ordered pairs to get the inverse. Okay, I forgot what I was going to say there. A senior moment. Okay, but I want to find the derivative of this thing. Okay, so y is the arc cosine of x. Here's a picture of our function. We know what its domain and range are. And okay, I don't know what the derivative of this is, but I can take the cosine of both sides. In fact, the cap cosine. My one-to-one cut down version of the cosine. And now these arc cosine and cap cosine are inverse functions. So one undoes the other. That means I just get x on the right-hand side. Now I have y defined implicitly as a function of x. And that means I can differentiate implicitly. Okay, but y is the function. X is the independent variable. Y is a function. Okay. Well, the derivative of x with respect to itself is 1. The derivative of the cosine of y, okay, and the fact that I cut down the regular cosine to get this cap cosine, that does not affect what the derivative is. The derivative is still minus the sine of y, but because y is a function and not just an independent variable, chain rule says I've got to multiply by y prime. And now we've got that y prime is minus 1 over the sine of y. Well, the cosine of y was equal to x. Draw my triangle. And cosine is adjacent over hypotenuse. If the cosine of y is x, I can label my triangle as opposite side, or adjacent side rather. Adjacent side is x, hypotenuse is 1, and that means that the opposite side is the square root of 1 minus x squared. Okay. And that means that, okay, rather than writing y prime in terms of y, I can get it back to in terms of x. The sine of y is that square root of 1 minus x squared over 1. So And that's just 1 over the square root of 1 minus x squared. Okay, so that says, well, remember we had that the derivative of the arc sine and the derivative of the arc cosine is just minus that. And this relationship is essentially why you rarely see the arc cosine. It's a perfectly nice function, but because the derivatives have this relationship, usually people will just refer to this. And yeah. Oh, my stomach is growling. After we do derivatives and we talk about how you use derivatives to do graphs and to do optimization problems and a lot of things, we're going to talk about anti-derivatives. So the fact that these two derivatives are related this way is really important. In a similar way, okay, the arc tangent, then the arc cotangent are related. Let's see, the cotangent, it has asymptotes at integer multiples of pi. And I don't really want yellow. Let's make it red. No. How about, okay. It looks like this. Okay. And of course you get to cut it down. So you keep this little piece. And the cotangent then, it has domain 0 to pi and range all the reals, which means that the arc cotangent has domain all the reals and range 0 to pi. And let's see if I can sketch it quickly. I'm going to flip the ordered pairs on that red curve. That's what an inverse does. Let's see, because the cotangent has asymptotes at 0 and pi, vertical asymptotes, that means that the arc cotangent is going to have horizontal asymptotes at 0 and pi. And let's see, and at pi over 2 goes through 0, so 0 goes through pi over 2. And, okay, so, no, curve like that. Yeah, okay. Yeah, my axis went away, okay. Okay, so it looks something like that, okay. And then, well, okay, so we have y equal to the arc cotangent. Take the cotangent of both sides. And we took the arc cotangent of x, and then we took the inverse of the arc cotangent of x. That just undoes what we did. So kept cotangent of y is x. The derivative of cotangent is still minus the cosecant squared of y. Y is a function, so I have to use the chain rule. Derivative of x with respect to x is 1. Y prime is minus 1 over the cosecant squared of y. And then do my triangle. Okay. Cotangent of y is x. Cotangent is adjacent over opposite. So I can label my triangle like that. The hypotenuse is the square root of 1 plus x squared. And okay, the cosecant is hypotenuse over opposite. So that's going to be the square root of 1 plus x squared and squared. Okay, so the derivative of the arc cotangent is minus 1 over 1 plus x squared. And that means that the derivative of the arctangent, oh, I'm almost out of time. The derivative of the arctangent is 1 over 1 plus x squared, and that's equal to minus the derivative of the arc cotangent. Okay. So everybody agrees pretty much on how to cut these 4 functions down to have an inverse. With the secant, you're not so lucky. Okay, with the secant and the arcsecant, some people do it differently. The secant, okay, looks like this. That's minus 1, 1, and okay, does not touch the asymptote, of course. So again, it's periodic. What do you keep to make it 1 to 1? How do you cut it down? Well, everybody pretty much agrees you should keep this piece. But what about the negative piece? Well, some people keep this piece, and other people keep this piece. So, okay, so, and it kind of does make a difference in some context, but I am out of time, so let me stop there. We will start with the arcsecant tomorrow, but now we have the derivatives of a new batch of functions, okay? We have the derivative of the arc sine, and that's minus the derivative of the arc cosine, and we have the derivative of the arc tangent, and that's minus the derivative of the arc cotangent. Okay, any questions? I'm going to go back to my unshared screen. Okay, you can go because I'm out of time. And hang around if you have questions.
Have a good day.
You too.
Bye.